Good morning, everybody, and welcome to week 10 of our 15-week CWS preparation webinar series. We are, after today, 2/3 of the way through. Yay! We're almost there. So let's get started on today and keep working our way through. Today we're going to talk about water potability, disinfection, and water analysis. First and foremost, I want to say thank you. I appreciate very much the opportunity to serve you guys in this way, as always. And it's always my goal to make sure that the information that I give to you is at least as valuable as the time you're giving to me. I definitely appreciate it. So thank you very much. Today what we're going to talk about, the Safe Drinking Water Act, and we talked a little bit about that early on, like 10 weeks ago, 2.5 months ago. We are going to go back and review that a little bit. Living stuff in the water, how to disinfect stuff, odor and taste, a little bit more on depth filters, and then we're going to talk about water analysis. So let's go back to the Safe Drinking Water Act. It was passed in 1974. And it basically established community public water systems and the rules for what they are, okay, and how you would categorize them. Basically, the CWSs serve year-round residents. Those include municipal systems, mobile home parks, apartment buildings, condominiums, with their own water source serving 25 or more residents. Then you have the non-transient, non-community public water systems. These are entities having their own water supply, serving an average of at least 25 people who don't live at the location, but who use the water for more than 6 months a year, so schools, churches, factories, office buildings. Transit non-community public water systems, these have their own supply, but they have at least 25 people they visit and use the water occasionally, but only for short periods of time. So those are parks, motels, hotels, and restaurants. Make sure everybody's muted here so I don't get the background noise. Safe Drinking Water Act regulates approximately 220,000 public water systems. They are categorized as very small systems, which is less than 500 customers. So you see that even an office building that has more than 25 but less than 500 would be considered a municipal system and would be regulated under the Safe Drinking Water Act. Small systems are anywhere from 501 to 3,300. Medium, 3,301 to 10,000. Large is 10,001 to 100,000. Very large, over 100,000. National drinking water regulations. There are two sets of standards that we look at. You've got the maximum contaminant level. These are the minimum drinking water requirements, or the maximum amount that you're allowed to have in the water in a certain substance. Okay, those are the MCLs. And then you have the MCLG, which is the goal. So here's an example. Arsenic, the maximum contaminant level for arsenic is 10 parts per billion. That is the maximum contaminant level. You're not allowed to have more than 10 parts per billion of arsenic in the water. The goal is 0 or non-detectable. That's the goal. Okay. Same thing with nitrates or coliform. Coliform is you're not coliform bacteria. You're only allowed to have the goal is 0. No coliform in the water. But the maximum contaminant level is 5% of the sample, so 5 out of 100 can have coliform in the water. That's the maximum contaminant level. Then you also have the secondary drinking water regulations, and this is where these are not safe or unsafe issues. They're more aesthetics of the water. So, for example, total dissolved solids. The EPA, the Safe Drinking Water Act, says that they recommend the water could be of better aesthetic quality if it were over 500 or less than 500 parts per million of total dissolved solids. But they're not going to fail a well or fine them if they're over 500 parts per million total dissolved solids. They're just saying that that's the recommendation. Okay. Lower life in the water is some of the stuff that might be bad. Bacteria, protozoa, worms, viruses, fungi or fungi or fungi or fungi. There's lots of different ways of saying it. However you say it, I think it makes you a fun guy. Wow, okay, that was bad. So not all the stuff in the water is bad. Some of it eats pollution. Let's talk about algae. Let's talk about algae, shall we? That sounds like something fun to talk about. So, okay, so these are single-celled or simple multicellular photosynthetic organisms. They produce their own food by using energy from sunlight to synthesize complex molecules from carbon dioxide and water. That's called photosynthesis. It exists both in sea and fresh water, but it likes stagnant, warm surface water. It has caused the death of cattle. So here's the thing. Hopefully in each class you guys sit through, you learn at least one thing. So here's what I hope that you'll take from today. If you're out there walking through the woods somewhere and you come across a pond and it's got a bunch of green stuff all over the top of it, and there are cows laying dead alongside the pond, I wouldn't drink it without water treatment, without some sort of treatment, okay? Just saying that that's a suggestion, something that you might want to take from this class, is that if you have a bunch of dead cows laying around a pond with a bunch of green stuff on top, don't drink the water without first treating it. I'm here to help you guys. Okay, so fungi comes in many different varieties: molds, mildew, mushrooms, yeast, smut, which I think is awesome that smut is actually a real word, because when I was in elementary school, I got in trouble for saying the word smut, and I don't think the teacher knew that it was, smut, and there. Now, she can't do anything about it, and I'm totally feeling way better about stuff too. So I don't remember her name. I just remember I got in trouble for saying smut. It apparently was a bad word. But it cannot. Fungi cannot produce their own food. They help break down dead organisms. They're usually, but not always, colorless. Okay, diatoms. Now diatoms, these guys are in water. They actually pop back up in water treatment, because if you if you take the advanced certification course, which we offer, by the way, it's a lot less. The diatoms, you're going to see something. A lot of filter medias, a lot of filters use diatomaceous earth, and diatomaceous earth comes from crushed shells of diatoms. So these little guys right here, they actually are what make up diatomaceous earth. So they're algal protists. There are more than 15,000 types. They can give water a fishy taste, sort of like anion resin has a fishy taste, or a fishy smell. These guys will give water a fishy taste. Mold is a type of fungi. It exists ideally in water that is 80 degrees Fahrenheit to 100 degrees Fahrenheit. It's generally a strong indicator of heavy pollution in the water if you have a lot of mold around. All right, now this is the creepy stuff, bacteria. All right, this is going to freak you guys out a little bit here. All right, as we talk about bacteria, it's kind of creepy. This is creepy stuff. Okay, so 1 to 10 microns in length and 0.2 to 1 micron in width. The total weight of all bacteria is more than all other organisms combined on Earth. So like the total weight of all the bacteria that we have on this Earth, and here's the thing that's a little creepy about that. If these guys got together, I mean, they reproduce like crazy. I mean, they're just constantly just, making more of themselves. They just like constantly reproduce. And if they got together, think about this. The total weight of all bacteria more than all other organisms on Earth combined. So even if a portion of them got together and they formed this huge, gigantic bacteria monster, and it's like if it got together, it could be like, like Godzilla in Tokyo, and just walking through the, this big, huge bacteria. It has to be stopped. We cannot allow the bacteria monster to get, it's huge. There's nothing on Earth that could stop it. All other living organisms wouldn't be as big as the bacteria monster. It's a problem, people. And that's the second thing that you can take from the CWS course. They do decompose stuff too. So the bacteria monster, it would just come by and it would just like instant decomposition. They can be harmful or helpful, and it's time to start recruiting good bacteria now to fight the bad bacteria monster. They could be like Godzilla versus King Kong, you know, except the one where King Kong wins, right? Okay. They are sensitive to pH and temperature of water. Worms, there probably won't be any questions about bacteria monster on the exam. I'm just saying that while I believe there should be questions about the bacteria monster on the exam, there probably won't be. But, you know, it is what it is. Okay, you guys are forewarned now. Worms belong to the animal kingdom. There are flatworms and nematodes, or roundworms, rotifers. And except for rotifers, they're mostly found on the bottom of lakes and streams. Rotifers live in stagnant fresh water. They can be filtered out easily because of their size, and they are important scavengers. Protozoa are one-celled organisms that live near the surface or very deep. They live as parasites, and they give water a fishy taste or odor. They can be either aerobic or anaerobic. And Giardia lamblia and Cryptosporidium cyst are examples of these. So the Cryptosporidium, you may recognize that from in Milwaukee back in the, I think it was 1990 or 1991. A bunch of people got sick and died, or some of them died and a lot of them got sick because of the Cryptosporidium cyst that was in water. These guys are actually fairly easy to remove from the water. The Cryptosporidium, in fact, most of your point of use, even your pitchers, your pour-through pitchers, most of them are certified to take out the Cryptosporidium cyst and the protozoa. Nematodes belong to the worm family. When found in warm-blooded animals, they're big enough to be seen, but they're microscopic when they live in fresh water or the soil. They produce a bad taste and odor. And a lot of them carry disease-causing bacteria. See, bacteria use other things to spread. This is something that, you know, I'm in therapy about all this, so it is, but not because it's not real, people, not because it's not real. Okay, and I'm not really in therapy over it, but it's been suggested that possibly it could help. Okay, so the nematodes are found most commonly in municipal water, and they're derived from municipal water derived from a surface water source. Viruses, now these guys are kind of nasty things. They're the smallest of the infectious organisms, and they're too small to be seen with the microscope. They're too small to be seen without a microscope. That's a typo. And they'll pass through many filters. They're bad for the drinking water. Not good. Viruses are not good. Not good. The problem with a lot of the stuff that we run into, the organics and the stuff that can make the water non-potable, is that it's tough to detect because there could be a lot of different things in one supply. So just when you think that you got one thing figured out, you know, that's causing the trouble, it may be something else in the water that is doing it additionally. And the more people a water supply serves, the more tests have to be taken. And that is part of the Safe Drinking Water Act. So there are more stringent requirements on a municipality that can afford it than there are on the smaller ones. People on private wells rarely have their water tested, although they should, because you know, stuff gets in the water. So a lot of people, they move into the house and it's required testing, so they have it tested when they first move into the house. But a lot of times, even that's just coliform and nitrates, and it's not even all the other stuff. They should really have their water tested usually once a year if you found nitrates or bacteria in any positive samples ever, or once every 3 years as a minimum. Okay, coliform bacteria, we talked a little bit about that. Coliform bacteria is not actual poop bacteria or fecal bacteria. It's not, I will tell you, it is fun to teach a class and say poop. It is, again, it's like I could teach a whole class just going the whole time just saying smut and poop, and there's nothing my fourth grade elementary school teacher can do about it, because she just can't. But anyway, coliform bacteria, they're strong indicators that there's fecal contamination. That's guilt by association. It's not actually the poop bacteria. It just exists where poop bacteria exists. Okay? And that's because they cannot live outside of a warm-blooded animal. So they start to die off. And EPA, this is the kind of a little scary thing, is that EPA says no more than 5% of the samples are allowed to be contaminated. That means that it's acceptable if you have 100 samples and 5 of them have coliform in there, then that's acceptable. The goal is 0, by the way. I mean, they don't want any in there, because coliform usually if there's coliform, then in the water, then it's a good indication that there's fecal bacteria there. So, and fecal bacteria is bad for you. But now I'll tell you, like it's not uncommon for a well, or if you're taking a sample, for it to come back positive for coliform. People get all freaked out. Oh, I got bacteria in my water. Well, yeah, a lot of people do. But a lot of times it comes straight from the sampling, taking the sample, actually taking the water sample, and that's because you probably have coliform bacteria on your fingers right now. I mean, normally it comes from not rinsing the bottles or disinfecting the nozzle, the spigot where you take the sample. But and then you touch the lip of that, or if you have coliform. And in fact, do this just as a sample. Everybody, take your fingers and put them in your mouths right now. Put them in and lick your fingers. Lick your fingers. Just suck on your fingers a little bit. Suck on them a little bit right now. Okay, I'll wait. All right, good. You just probably ate coliform. You have probably had coliform on your fingers right there. So if you really did it, if you really stuck your fingers in your mouth, and who wouldn't, because you guys all, it's part of the class requirement, right? You all did it, and so you just ate coliform. You just ate coliform. You just ate coliform. But I wouldn't. Maybe that's what I got in trouble for, was taunting other people. I don't remember. Maybe the whole lines back then are blurred. I try and put it out of my mind. I start thinking about that, and I start thinking of Kelly, big fat belly, rolling jelly, ha, I get a girl's name, and next thing you know, I'm crying in the corner, and having to miss recess because I'm too upset to play with the other children. Anyway, let's go to the next slide. So water disinfection should be able to destroy all types of pathogens in whatever number is present in the water. They should destroy pathogens within the time available for disinfection. A disinfectant should function properly regardless of any fluctuations in the composition of the water. A disinfectant should function within the temperature range of the water. A disinfectant should not cause the water to become toxic or unpalatable. A disinfectant should be safe and easy to handle, and it should be such that it's easy to determine its concentration in the water. A disinfectant should provide residual protection against recontamination. Not all of them do, but they should. Boiling water is a way of disinfecting the water, and you should boil the water. Here's what I'm talking about in terms of residual. Once you boil the water, it cools back down. You're no longer disinfecting the water. You should boil it for at least 1 minute. You'll probably see that again somewhere. Water should boil for at least 1 minute before you, in order to disinfect, properly disinfect. So I would keep that 1 minute time period in mind. No important waterborne diseases are caused by heat-resisting organisms. UV light imitates nature, right? It's all part of, we talked early on in this class how nature does all the water treatment first. I mean, basically most of the treatment that we do imitates nature. I mean, nature does it first. We sometimes just do it a little differently, but we basically use the same concepts. So it imitates nature, so UV rays from the sun. In order for UV to work effectively, you must be free of turbidity and color. It does not add taste or odor to the water, and there's no residual effect on this one either. The light does gradually lose power, so a lot of them will have an alarm on them that tells you when it's losing power, but just because it's lit up doesn't mean that it's working. The light's got to have enough power, enough UV rays to penetrate and disinfect. And if you have any turbidity or any color in the water, that light's not going to penetrate, and it's not going to kill all the bacteria. Also, when you have things like Giardia, Cryptosporidium, when you have the cyst in water, those things have shells around them, like protective shells, and so the UV takes a lot more actually to kill them because it's like they have a shield on them, so they go right through there, and they're like, UV, I'm wearing sunscreen, ha ha. So, okay. Bromine. Bromine is an oxidizing agent used for swimming pools. It doesn't cause eye irritation or a bad odor. Chlorine is one of the most widely used disinfectants throughout the world. It comes in a couple different forms. You got the sodium hypochlorite, that's household bleach. It's usually 5.25% chlorine. And the calcium hypochlorite is the dry granules. That's about 70%. I'll tell you what is fun is to open up one of the containers of the pellets of those dry granules and just stick your nose in there and take a big whiff. Woo! If you're at the office and you have some of those back, go try that right now. I won't wait for you because you'll probably go to the hospital if you take a huge whiff, because it will burn your nose and lungs and you won't be able to breathe the rest of the day. So maybe you shouldn't do that. Maybe if there's like a neighbor or an ex-in-law or something that could do it and then get back with you on its effects, that would probably suffice. Not that I would recommend, nor would Moti-Vitality, nor does the Water Quality Association sanction trying to get neighbors or ex-in-laws or anybody that you don't like, pets, kids, anybody to sniff 70% calcium hypochlorite bleach. That's not appropriate, so don't do that. Okay, usually it's fed by a chemical feed pump of some type. The thing with chlorine is it always results in trihalomethane, which are a known carcinogen, and they also are known to cause adverse birth outcomes and cancerous. So here's the thing with chlorine. It's an excellent disinfectant. It does kill the bad stuff in the water, okay? And it does have a residual. It stays in the water. And, it continues killing long after it's killed. So it's the killing that keeps on killing. But it's a good idea to take it out. When it gets to the house and you no longer need it in there and you're ready to drink the water, it's a good idea to pull that stuff out of the water. It's a VOC. It does absorb through the skin. And here's a cool little interesting experiment sometime. Take a cup of RO water and pour a little bit of bleach in there and do a chlorine test. Just do a chlorine test. Now stick your fingers in there and hold them in there for 30 seconds, and now do the chlorine test again. The chlorine's gone. It's going to be lower because it absorbed in through your skin. So that's not good. It's a good idea. Chlorine should come out of the water once it comes into the house. You should take the chlorine out of the water. Now, all of that being said, don't go out there and start scaring people, your customers. Don't go out there. Well, Kelly said that chlorine will kill you and it causes cancer and birth effects. Are you pregnant, lady? Oh, I'm sorry. How embarrassing. You're not. Well, if you were, it could cause birth defects if you had a kid. So if you ever do get pregnant, which I doubt because, look at you, then that could cause adverse birth outcomes. I wouldn't say any of that to your customer. Not a good idea. Especially if you make a living based on sales results. But there's enough research, you can point people directions where they can learn it on their own to kind of see that that they don't need that chlorine. They don't want that chlorine in the water. So let them do their own research. Okay, So the parts of chlorine that are relevant when it comes to adding chlorine to the water, you've got the chlorine demand. That's the amount of chlorine which will be reduced or consumed in the process of oxidizing the impurities in the water. So basically, you have so many, impurities there, and the chlorine is going to go in and kill those. Whatever it takes to kill the stuff that's in the water, to oxidize it or to disinfect it, that's the demand. The chlorine dosage is the total amount of chlorine fed into the water, and then the residual is what's left over after it's killed the bacteria and all the other stuff in there. Okay? So it's the amount of chlorine still remaining in the water after the oxidation takes place. Iodine is used in emergency situations. When I was in the service, we used to carry around these little pills, and so if we had a stream or whatever, then we didn't have time to boil the water, or any way to boil the water, then we'd drop a little iodine pill in there and it would disinfect the water. So it's only used in an emergency situation, but there's not enough known about iodine in the human system, so it's not commonly used. Copper kills algae, but it's not very good for bacteria. Alkalides and acids, disease-causing bacteria don't like high or low pH. A little bit more on chlorine disinfection. It's best if the pH is 6 to 7. Jim's saying iodine, we do know enough about it, so we don't use it. Oh, so we don't. I think Jim's saying we don't know enough about it, so we don't use it. That you might see that again somewhere, something similar. That you don't. Okay, so it's best if pH is 6 to 7 on chlorine disinfection. Disinfection is better with longer contact time. Superchlorination, dun da da da, it's superchlorination, which, now that I think about it, could be superchlorination man. That is the guy that saves us from the bacteria monster, because it's like Superman, except he's a chlorination guy. And anyway, just thinking, I'm preparing for all of you. I'm here to serve the industry and the world. Okay, superchlorination is a means to achieve greater disinfection with shorter contact times. What it actually means is that you load the heck out of it with chlorine, and because there's so much of it, it kills stuff a lot faster. There are two components of a chlorine injector, or a chlorinator. You've got the chlorine injector, and then you got to have the dechlorinator, because again, you got to take this stuff out of the water. So it should happen before the retention tank, and that's because the retention tank gives that contact time, gives it extra contact time. Okay, palatability, taste, and odor. Water should be free of detectable taste or odors, should be free of turbidity, sediment, and color. There are only 4 tastes in existence. We've got sour. Everything out there is either sour, salty, or saline, sweet, and bitter. 4 tastes. There are lots of different odors or smells. Nasturtium, cucumber, geranium, fishy, pigpen, Taco Bell. Oh, no, that one's not one of the official ones. I'm sorry. Earthy, grassy, musty. Taco Bell should be on there because it really does have its own distinct odor, don't you think? And then there's Taco Bell, and then there's Taco Bell. There's like Taco Bell 4 hours after Taco Bell. And both of those should have their own odors. I think they should have their own odors listed. Maybe they do. Who knows? Okay, turbidity. Turbidity is the Taco Bell residual, right, Jim? Exactly. Turbidity is the measure of light that is scattered and absorbed by water because of the suspended matter in the water. So turbidity itself is not actually the mud and the debris and sediment and all that stuff in the water. In fact, water could be clear. It could have no debris or sediment in it at all and still be really turbid water. What turbidity is the measure of light that's absorbed by the water. Turbidity is the lack of clarity or the brilliance in the water. It may have a great deal of color. It may even be dark brown and still be without suspended matter. Coffee is an example, or tea. Okay, that's turbid water because you don't, unless you have grounds in it, it's going to not have sediment or debris in it, but it's not going to absorb light. Suspended matter can be removed by mechanical filtration, and if it is, turbidity is caused by suspended matter. Municipal plant may use a coagulant like aluminum sulfate, which basically clumps it all together so it can be filtered out and settled. You can use a multimedia depth filter for whole house treatment. Now, the color of the water is generally blue or green, but it should be colorless in the home. Color in the water is usually caused by vegetation. That's called tannins. Except when used in some commercial applications, color is usually aesthetic. Now, I'll give you guys a little hint, a little serious secret on how to check whether or not you have tannins in the water using tools you probably have in your test kit. See, they do make tannin test kits. There's a problem water test kit that you can buy that will test for things that you normally wouldn't test for. And there are tannin test kits out there. But here's the issue. Okay, tannins will cause, it will look like somebody peed in the water. It makes the water kind of a yellowish, sometimes a greenish tint to it, and it's harmless. It's not going to hurt anything except aesthetic, other than you fill up a big white bathtub and it looks like somebody peed in it, and that's aesthetically. People don't like that. So you can determine whether or not it's tannins in the water, because the thing is, if you have a little bit of oxidized iron in the water, then that will also cause the water to have a yellowish tint. So how do you determine whether or not it's tannins or oxidized iron? Well, because here's the problem also, is that tannins will show up on a lot of the iron tests out there. Tannins will show up as iron when you test them. It will show up positive for iron. So here's how you determine whether or not you have actual tannins in the water or iron. So most of you have a little mini water conditioner in your test kits. Hopefully you also have these little, and if you don't, you can buy them. They're dirt cheap. Just these little 1 micron pleated filters. And the 1 micron pleated, they're pleated filters. You can order those, and I would have a few of those in your test kit for things like this. Okay. But what you do is you test your water. So let's say that you test the water and you've got 2 parts per million of iron in the water. Now we need to determine whether or not, and the water has a yellowish tint to it. Now we need to determine whether or not that's oxidized iron, any of that's oxidized iron in the water. Okay, so the way we do that is we run that water, run your raw water through your mini water softener. Now you recheck for iron again. Let's say you still have almost a part per million of iron in the water after the water softener. Now, that is either going to, we know that all the clear water iron has been removed from the little water softener, the little mini water softener, because the water softener will remove the clear water iron, the ferrous iron. So what's left is, say, 0.9 parts per million of what looks like iron. And the water does have this yellowish tint to it. So now we need to determine whether it's tannins or whether it's iron, because they're going to be treated differently. We're going to treat them differently. Tannins will be treated with an anion resin. Irons could be treated with an iron filter, some kind of an oxidizing filter or whatever. So we need to, and the thing is, you cannot oxidize, not with a closed pressure aeration system anyway, if you have organics in the water, because all you're doing is pumping oxygen in and giving bacteria tons of food and creating, a breeding ground for that bacteria monster. So what you do is you take this 0.9, the softened water that's run through the mini with 0.9 parts per million of iron in it. Now you run it through these little 1 micron pleated filters. If you by chance do not have the 1 micron pleated filters, then get 5 coffee filters. Okay, and probably the customer will have those, or you may have those. It may be easier for you to acquire those than the 1 micron pleated. But get 5 coffee filters and layer them. Now run your softened water through those 5 filters and into a thoroughly rinsed out test tube, and it's going to be slow. It's going to drip through those filters very slowly. Now let it drip into that test tube and retest for your iron. If you still have iron in the water, or if your test still shows iron, and after you've run it through that 1 micron filter, then odds are pretty good that you have organics in the water or tannins in the water. If you don't have, and that's because that filter, the 1 micron filter, will remove any oxidized iron. It will filter it out. So if it's still showing up as iron, then you've probably got tannins in the water. So that's just a quick little, easy little field test to tell whether or not you have organics or tannins in the water. All right, water analysis. Now, the water analysis that we're going to see here, these guys came out of the book and are ancient. I mean, they're like really old. And I actually have another, like a real one, a real water analysis report on my laptop, but I had to borrow Jen's laptop today because my laptop is temporarily kaput. So so I'm using her laptop today, so I don't have it. So we are going to see some water analysis. The thing with the water analysis, it is important to recognize these. Now, one of the best places you're going to see one or get one, and in fact, the one that you're probably going to run into the most is going to come with the consumer confidence report that is required by law for all municipalities to have available to their customers. Okay, so by law, the water analysis reports and a breakdown has to be available to the consumers. That's in the CCR, Consumer Confidence Report. I would strongly recommend that you go down to your municipality, get a hold of this thing. You can also find a lot of them online on the internet. Find the Consumer Confidence Report, learn it, study it, know what it is. That way when your customer hands you one and say, can you explain to me what all this stuff is, you're not looking at it for the first time. You can say to them, oh yeah, that's the Consumer Confidence Report. Let me explain to you what it is. Because then you become an expert. You look like an expert in your field, which you should be. That's part of what you're getting certified here for, right? And then you need to learn how to troubleshoot underwater analysis also, to recognize what could cause problems, to recognize what's on them, and to know how to treat them. So first thing, start with the senses. I mean, your nose and your eyes and your tongue, they're going to actually tell you a lot about the water. So that's the first place to start. Water analysis beyond that is best and most accurate if it's done by a lab. Regular testing is required for municipal supplies, but not for private wells. Private wells should be tested for coliform at least once a year and nitrates every 2 to 3 years. If nitrates are detected, they should be tested at least once per year. Other tests that are recommended, and hey, look, these are some that we do. Water hardness, iron, manganese, hydrogen sulfide, total dissolved solids, chloride, fluoride, sulfate, heavy metals, radon, pH, alkalinity, dissolved oxygen, turbidity, chlorine and chloramines, lead, and copper. Speaking of heavy metals, I heard yesterday that Striper is getting back together, or that has gotten back together. Striper. Do you remember Striper from the 80s? Wow. The car that we rented has a satellite, and we were listening to Hair Nation. That's Jen's favorite. She likes Hair Nation. VOCs should also be tested for. Pesticides, herbicides, protozoan cysts. Okay, so let's talk about the water analysis. Like I said, these came straight out of the book, and so the sample, when you take a sample, should be, the analysis should be done on it pretty quickly. Okay, the sample needs to be taken properly, use a clean container, and document everything possible about the sample source. Okay, document it. So the date and time it was taken, whether it was hot or cold water, whether it was outside. I mean, the more information is power. So, was it soft water? Was it hard water? Is there equipment in the home? Is there, how often is the house used, the water used? I mean, every information, more information you can write about a water sample, the better, the better the results are going to be when it comes to the testing. All right, so here's one of the samples that came out of the book. So first and foremost, the problem with this one is that it was collected August 14, 1983. That's, what, 30 years ago? It sort of dates this book, doesn't it? So we're going to assume that this was not taken. Let's say August. We'll say it was, you know, just recently. We're going to pretend that it was more recent than this. Okay, but the source is a well. Notice that it is, 9 days that the sample was tested after? I mean, that's a problem. So it really needs to be done sooner than that. But what kinds of problems, what are we going to run into here? Anybody, I'm going to let you guys chat a little bit here and tell me what are we looking for? What kind of problems are we running into, and what do we need to do to fix it? So what are some of the things that we're noticing here? What's the problem with this one? Anything here that we need to take care of? Hardness, okay. Notice that the values are reported as CaCO3. That is the case, that's going to be the case on the water analysis that you get out there from the cities. The biggest difference is that you're probably going to see it as parts per million. Okay, so this water analysis is listing it as grains per gallon. It's probably not going to be grains per gallon on your lab results. It's going to be in parts per million. So somebody tell me, what would be the parts per million in this one? What the total hardness? What would be the amount of parts per million on this if you saw this on a real lab? Somebody calculate this for me real quick. So we're looking at total hardness. So we've got 15.8 grains per gallon of total hardness. What is the? How do we convert that to parts per million? And you will see this again on the exam. But how do you convert that 15.8 grains per gallon to parts per million? Good. Thank you, John. Excellent. Multiply it. That's right. That's right. Multiply that. You're going to multiply that 15.8 grains per gallon by 17.1. You will see that again. I can almost assure you. Okay, so 17.1. So when you see that water analysis out there, and it's showing your total hardness, it will say hardness as CaCO3 or calcium bicarbonate. When you see it that way, you're probably going to need to divide that number by 17.1, and that's going to give you your hardness. Okay, if you see grains per gallon, you're going to multiply it by 17.1 to give you your parts per million. Okay. Yeah, and you will, the 17.1 number, you're going to use, this is something that you will use a lot in the field. Jen's right. It is relevant. Oops. Okay, so yes, we have hardness here that we're dealing with that we got to take care of, the total hardness. And 1 grain per gallon equals 17.1 parts per million. So that's going to give us approximately 270 parts per million on this analysis here. All right, so yeah, it's the hardness. We do have a slightly high pH, but looking at this, mostly it's just the hardness that we're going to have to take care of on this one. Okay, water analysis number 2. What are some of the problems that we have here? What are we going to deal with here? What do we have? Anything that jumps out at you as a concern here? Anybody? Yep, we definitely have iron. A lot of iron. 2.6 parts per million of iron, in fact. That's a lot, the problem. And in fact, looking at this analysis, my guess is that you might have some oxidized iron in the water. And the reason I'm going to guess that is, what makes me think that we might have some oxidized iron in the water, possibly? Here, what would be a good indication that there's possibly some oxidized iron? Anybody have a guess? Well, yep, it is appearance when drawn. It's got a clear, that's right. It's got a yellowish color, that's right. What else? We have a pH of 8. Okay, so usually clear water iron, it stays clear water if your pH is slightly lower, acidic, because it stays dissolved. With the pH of 8, you have an excess, usually, of hydroxide in the water. So that could be, those extra hydroxides could be sticking some of that iron and causing it to convert from its ferrous form to its ferric form. Okay, so we need to bring the pH down. Also, the pH is pretty high. 8 is pretty high there. Iron is definitely high. We do have hardness here. Now, one of the problems that we might have a hard time with here, there's another issue here, is remember you have to have 2 or 3 grains of hardness for every part per million of iron in order for ion exchange to work. So probably you're going to end up needing an iron filter on this system to oxidize the rest of it and filter all that stuff out. Okay, so it's definitely heavy iron. Also, in terms of color, the US EPA secondary drinking water limit is 15 units of color, so we got to get rid of that color. Now, filtering out the iron, if it is in fact caused by oxidized iron, then putting an iron filter in is going to get rid of the color as well. All right, water analysis 3. What do we notice here? Anything we're noticing here? What's the problems that we're running into here? pH, yeah, we definitely have a high pH. We're fortunate we don't have a lot of iron. Remember, 0.3 parts per million of iron will cause staining. 0.3, we're only at 0.2 here. We definitely have hardness here. Yeah, total hardness 24.1 grains per gallon of hardness. We definitely have hardness. Anybody see anything else? If you read the books, is there anything else here that you see that might be a problem? There's definitely a high pH, so we're going to need to bring that pH down using some sort of a citric acid or something like that. But then the sodium sulfate may also cause a laxative effect. So there's high enough sodium sulfates here that they may get some diarrhea until their body. Wow, this has been a fun webinar. I get to say smut, poop, and diarrhea. This is bringing out my inner elementary school kid. Wow, I feel really good. Anyway, sodium may cause problems with obtaining zero soft water. If you have a lot of sodium in the water there, it becomes a little more of a challenge because that sodium is competing with the resin or with the calcium. So basically, it's trying to regenerate as it's softening. So the resin has to make a decision between the calcium and the sodium as it's taking that stuff out. So it could be a little bit more of a challenge as well. That, everybody, is week 10. Week 10. So next week we're going to be talking about drinking water systems. So you get to learn a lot about reverse osmosis and distillers and all that good stuff next week. So anybody have any questions? Any comments, questions, anything? All right. Well, with that, then everybody have. Oh wait. We do have a question here. Sodium sulfates. Is that what we say referred to as sulfates? Yes. Yeah. Sulfates, sulfides. Yes, we would. Yep. So yeah. Yes, that is Pete. That is what we would refer to as. Okay. Anybody else? Let's go back. Let's look. Bicarbonates. Let's go back. They've got the bicarbonates listed there as hardness. So, yes. I mean, you mean the calcium bicarbonate and magnesium bicarbonate? Most of that would come out with a softener. So those compounds would mostly be removed through the water softener. Well, remember calcium. That's dissolved. That stuff is the bicarbonate is the dissolved rock in the water. So those are the magnesium, the calcium, all that stuff is going to come out. The bicarbonates themselves are going to be an issue if you are working on the alkalinity, and probably it's because you've got high alkalinity here because of the bicarbonates. Okay, the alkali taste. All of that is there, so you can get rid of those. They're just the elements, well, it's carbonates and bicarbonates. yes, they are elements of the hardness, but it's the second part of the compound. So those are the bicarbonates are going to be high there. They are what's causing the high pH or the high alkalinity. You know, the alkalinity systems you see out there, they function and work. They raise the pH and the alkalinity by adding bicarbonates to the water, along with other stuff. So what the bicarbonates are going to do is they're going to give you a high pH, and they're going to give you that soda taste. So you've got to really, if you looked at the total dissolved solids, which they don't have listed here, you're going to have really, really high total dissolved solids on this. I mean, just if you looked at all the stuff measured here in grains per gallon, so it's correct to say that the carbonates are elements of hardness in the bicarbonates. I'd say it's all part of the hardness. I mean, I would say that that's an accurate statement, but both the carbonates and the bicarbonates are hardness, and the carbonates or the alkalinity is going to be different. It's all going to be contributing. So, you know, calcium bicarbonate, remember, that's dissolved rock. Okay. You know, that's the hardness. That is the hardness, but it's both components of that make up the hardness. Okay. All right. Okay, guys, I appreciate it. Thanks so much. Everybody have an awesome, awesome weekend. And if you happen to be in Kansas, we're in Kansas right now, live for the Kansas Water Quality Association. And so if you happen to be anywhere nearby, come by and say hello. We'll talk to you guys next week. Thanks. Bye.